Hi, Kevin and Hannah, feel free to turn your cameras off for now. Thank you. Still muted. Hi, everybody. Welcome today to another virtual VLA tour. I'm going to say good afternoon because that's where I am, and my team and I are here in Socorro, New Mexico. But as I see from the chat, I know some of you are joining us from all across the world. So good morning, good afternoon, good evening, whatever's appropriate for where you are. We're so excited that you're joining us today. My name is Summer Ash. I am the STEAM Education Manager for NRAO, the National Radio Astronomy Observatory. And I would just quickly like to introduce my team to you. So if Faith, Montana, and Tyler could turn on their videos, please. And Faith, if you would like to start by introducing yourself.
Hey everybody, I'm Faith Bowler. I'm the education specialist here at NRAO. I've been working here in Socorro as well for a little over 4 years now.
And Montana.
Hi, I'm Montana Williams. I'm a tour guide and I'm also a PhD student here in Socorro.
And Tyler, who you can see in the background of Montana's video.
Hi everyone, I'm Tyler. I'm also a PhD student here in Socorro and also a part-time tour guide.
Great, thanks guys. So Montana and Tyler will be active during the next 2 hours in the chat and in the Q&A. And Faith will be doing a presentation shortly. Faith, if you could advance the slide. I'd just like to give everybody an overview of today's event, just so you know what to expect. We're doing a special 2-hour event today. Our first hour will be our typical virtual VLA tour. So Faith will be giving a presentation on the history of the VLA, how it works, and some of our exciting plans for the future. After which we will have a guest operator come on and she and Faith will have a conversation, and then everyone will get a chance to ask as many questions as they would like about the VLA. The second hour, we are going to have 4 very special guests and a panel discussion about 40 years of science with the VLA. And then we will have a second Q&A session with the STEAM Ed staff and the guest speakers, more specific to the topics that we will cover in the second hour. And finally, we will have a wrap up. We will give you some additional resources for if you would like to know more and follow more and keep up more with the VLA. And we will highlight our next tour for you. Next slide, please. Thanks, Faith. Today's operator is Hannah Brower. So that Hannah will be in conversation with Faith in our first hour. And the next slide, please. And our 4 special guests today are Amy Barger, Shami Chatterjee, Ron Eckers, and Kevin Marvel. So look forward to an hour from now when we get to hear a lot more about their experiences with the VLA over the past 40 years and the science that they do with it. So now I will hand it off to Faith, who will give you the inside scoop about our favorite telescope.
Thanks, Summer. All right, so yes, welcome to this celebration. The VLA turned 40 years old as of the day that we dedicated it last October 10th in 2020. So this entire year until the next October 10th is celebrating the VLA being 40 years old. And so today we're focusing on not on the science that's come out of the VLA by all of the amazing people who use it. And so before we get into the presentation, just some housekeeping details for all of you. So this webinar is going to be, or I guess normally it lasts an hour. Today it'll be more, it'll be closer to 2 hours. And if you have questions for us, please use the Zoom Q&A feature, which you can find right down here in your Zoom windows. And so we're going to have, as Summer mentioned, a couple of different sessions where we will be answering audience questions. But if you put your questions in the chat, it's very likely that they will get drowned out by other comments in the chat and we won't be able to see them. So please do use the Q&A feature if you have anything that you'd like to ask us. And some of the questions we will be answering in the Q&A window window, so you might get a typed response to your question, or others we will be saving to answer live during our Q&A sessions. Meanwhile, you can use the chat feature to interact with other audience members, and if we're having any kind of technical difficulties or there's something you need to let us know, like you can't hear us or there's some kind of issue, that's the place that you want to do that. And Montana is also going to be throughout our tour posting the links to a few different websites or features. So you can click there if you'd like to visit those. And all of the website links that we put in the chat are also going to be sent to you in an email that will be sent after the Zoom session. So if you miss it in the chat, don't worry, you'll still be able to access it. And make sure that your messages are send to everyone so that other members of the audience will be able to see what you have to say as well. And if you have any questions that you think of later, or if we're not able to answer your questions, sometimes we do get a lot of them and we're not able to respond to all of them. We also have an Ask an Astronomer feature on our website. And so you can search the archives right down here to see if the question that you have has already been asked before. And then if it hasn't, you can post your own question. And then typically the responses to those are posted within 72 hours, oftentimes less than that. So now we'll get into the details of the VLA and NRAO and what we do. So the National Radio Astronomy Observatory was founded in the 50s with the goal of building and operating observatories that study radio light that comes to us from space. So light comes to us in many different forms: visible or optical light, which is the kind that you can see with your eyes. And if you have just a backyard telescope that you can set up, it looks at optical light that comes to us from space. But we also have other types of light such as X-rays, infrared, ultraviolet. And so we are an organization that's dedicated to studying radio light. And we're funded by the National Science Foundation, NSF. And so that does mean that a small, but to us, very significant portion of your tax dollars go towards paying for the work that we do. And so that's why we think that it's very important to be able to bring the VLA to you. Even though we can't right now invite visitors to the VLA, at least find some way to be able to interact with audiences. And we have 3 different major observatories that we at NRAO operate. We have, of course, the Very Large Array, which we'll be talking about today. And then we also operate the Very Long Baseline Array, or VLBA, and work together with other observatories to operate ALMA, the Atacama Large Millimeter Submillimeter Array. So now we are going to, I'm going to briefly let Summer share an introductory video with you about the VLA. And bear with us while we set up the videos. It usually takes a second to get them running.
Coming very shortly. Okay. Share. Okay. Here we go.
Search for a perfect location for the Cornell Jansky Very Large Array, the plains of San Agustin in central New Mexico checked every box in a radio telescope site's needs. High, flat, dry, and rimmed with mountains to block man-made radio noise from the nearest cities. During the last ice age, this 45-mile-long, 12-mile-wide expanse was filled by an enormous lake. Now dry, it has seen thousands of years of human occupation, 100 years of cattle drives, and nearly half a century of world-class astrophysics research.
All right, and if the videos are a little choppy, please bear with us for that. That just tends to be, the internet is not always the best where we are, so sometimes it might not move totally smoothly, but we at least think the videos are a nice way to provide a an extra experience for all of you. So, so moving on to the next slide here. So the VLA consists of 27 antennas. Technically, we have 28 in total, but we're using 27 at any given time. Each of our antennas are about 90 feet or 10 stories tall, and the dishes are 82 feet or 25 meters in diameter. And we're located at a latitude of 34 degrees north. And so we can see about 72% of the total sky from where we're located. So that's pretty good. And that just means that the remaining 28% of the sky and the objects in it is too far south for us to be able to see. And so, as the video mentioned a little bit, we are built on the plains of San Augustine, an ancient lake bed. And so we started construction on the VLA in the 1970s. And as I mentioned before, we completed and dedicated it on October 10th, 1980. And so we chose this location because it's what we call high and dry. So when we're building telescopes here on Earth instead of up in space, we tend to look for those high and dry locations in general, because when the light is coming to us from space, the air in our atmosphere bends or distorts that light and makes it harder for us to see the objects that we're looking at. So if we build our telescopes at a higher elevation where the air is a little bit thinner, we can lessen that problem. So the VLA is at 7,000 feet or about 2,150 meters above sea level. And it's in the New Mexico desert, so pretty dry location there. And that's because, again, moisture in the air when there's a lot of humidity also tends to interfere with the light that comes to us from space. So by being in drier locations, we can lessen that problem as well. And as you can see in our image here, the plains where the VLA is located are also surrounded in most directions by mountain ranges. And that's really helpful because cities off in the distance like Albuquerque and Santa Fe, of course, have a lot of Wi-Fi and are sending a lot of radio signals. And the VLA is so powerful that it could easily detect signals from those cities and cities that are much further away as well. So these mountains act like a natural shielding from interference that we would get from civilization and from a lot of these cities. And so the VLA, out of these 20, like I said, 27 dishes we're using at any given time, we typically keep the 28th over at the antenna barn, which you can see in the upper picture here. And so we do regular maintenance on our antennas, and we cycle the different antennas in and out of our maintenance barn to make sure that they're working correctly and that the technology in them is up to date. And the VLA is operated on site. So we are located here, our staff is located in Socorro, New Mexico, but the VLA is about an hour west of here, and our VLA operators work out at the site to keep the VLA running. And so we'll talk more about that later when we get to talk with our operator. And so now about how the VLA works. So the antennas are arranged in a Y shape, as you can see from these pictures here, consists of a west arm and an east arm and a north arm. And so each of these three arms are made up of double sets of railroad tracks. And the west and east arms are 13 miles long of railroad tracks. And with the north arm, there's a ravine up at the end of the north arm that would have been really expensive to build a bridge over. So rather than doing that, we just shortened that arm a little bit. So that one is 11 miles long. And we have a total of 72 different stations on these three arms that can hold antennas. So it would be great if we just had 72 antennas, had one at each station. But as you can probably imagine, antennas that are this big are really expensive to build. So we built 28 of them because that's what we could afford to build. And so what we do instead is we rearrange these antennas to put them closer together or further apart, which allows us to zoom out or zoom in on our different targets. And so we have 4 main different configurations, as we call them, for how close or far apart these antennas are. And we were feeling very creative the day that we named these configurations. So we called them A, B, C, and D. So in the A configuration, the antennas are a long way away from each other. And so if you were to draw a circle around the outer edges of the antennas, then the diameter of that circle in the A configuration would be 22 miles or 36 kilometers. In the B configuration, it would be 7 miles or 11 kilometers in diameter. The C configuration, which is the one that we're in right now, is 2 miles or 3.5 kilometers in diameter. And then you have the D configuration when the antennas are darn close together, and that has a diameter of about 0.6 miles or 1 kilometer. And so this shows you just how big of a difference there is between the 4 configurations. So this teeny little white circle here at the middle is the D configuration. Then you have C here, and you have B, and the big white circle around the edges is the A configuration. And we go backwards in alphabetical order. So we go smallest to largest, so D to C to B to A, and then back down to D. And in terms of the zooming in and zooming out, you can think of it as big as small and small as big. So when we're in the smallest configuration, D, we're seeing the larger structures. We're the most zoomed out, so we can see the larger objects, larger structures that we're looking at. And then when we're in the largest A configuration, we're the most zoomed in. So we're seeing the highest resolution, the finest detail of the objects that we're looking at. And this is a great way of showing the differences between what you can see when you look at objects with different configurations. So this is looking at the active galaxy Hercules A. And so when you look at it with D and C, you can see the larger puffy cloud structures out at the edges of this quasar here. The diffuseness of these clouds, whereas when you look at it with B and especially with A, you see the finer details in the middle of those jets. And so when astronomers are asking to use the VLA, it's quite often that they might ask to use all 4 of the different configurations and then combine the data and that they get the images that they make together to get the best idea of what they're looking at. But it also just depends on what you're studying and what you want to learn more about. Maybe you're only really interested in those larger structures, so you might only need the C or D configurations, or maybe you do just want the finer details, and so you might just want A or B. So the 2 extremes, the A and D configurations, are our most commonly requested, but just in general, the VLA is in very high demand, which we'll also talk a little bit more about later. And so we normally move between these configurations every 4 months. So before September 2017, we were in a 16-month cycle where we would stay in each of the 4 configurations for equal amounts of time for 4 months before moving to the next one. And doing it in that 16-month cycle just guarantees that you don't always have the same configuration during the same season every year, so that because different objects are up in the sky during the day and during the night. So by changing it over time like that, maybe one time that you're in the B configuration, the object that you want to look at will be up in the nighttime, and then the next time you're in the B configuration, it might be up during the day. But since September 2017, we started doing this project called the VLA Sky Survey, or VLAS. And VLAS involves scanning and mapping the entire sky that the VLA can see a total of 3 times over the course of 8 years. So this project will be complete in 2025, and observing millions of different objects in the sky. And so the VLAS uses the B configuration, And so because of that, we want to make sure that we have enough time to do VLAS observations, but also still let other scientists and astronomers still use the B configuration. So we've now extended the amount of time that we use the B configuration every time. So we typically stay there about five or so months. And then in between moving to the B and the A configurations, we have a hybrid that we call BNA. And so in this special hybrid configuration, we have the west and east arms still in the B configuration, but we put the north arm in the A configuration. And so this hybrid configuration is used entirely to observe VLAS. So we stay in this hybrid configuration for typically about 2 or 3 weeks. And during that whole time, it's solely devoted to doing these VLAS observations. And then after that, we just move back into the A configuration. And so because of that, we still try to keep something close to a 16-month schedule. So we've been in the D, C, and A configurations for more like 3 months every time when we do this. And this is a totally public project. And so the data from VLAS, once it's been fully compiled, is completely available to the public. And so the link, the website for VLAS, where you can learn more about it and see the data that we've collected so far, is in the chat for anyone who would like to learn more about it. And when we move our antennas into these different configurations, we use our VLA transporters. And so we have, there are these 2 red machines here that are completely unique, and they were custom made to be able to carry our antennas. The VLA antennas weigh 230 tons, which is about 460,000 pounds. And so naturally, we needed to make special machines that would be able to pick them up. So they are able to just slide underneath them, unscrew them from the stations that they're currently plugged into, pick them up, carry them down the tracks, and then put them down at their new station. And each of the 72 stations that we have is fully equipped with all of the electronics and fiber optics that we need to plug the antennas in and connect them back to our supercomputer. So we don't have to bring along a bunch of electronics as well. When we move the antennas, we can just take them to their new station, plug them in, and pretty soon they will be ready to go. And so once we get them there, it takes a while to get them there because these transporters only have a maximum speed of 5 miles per hour or 8 kilometers per hour. And when they're carrying an antenna, they have to move even slower. We don't want them to go racing down the tracks and have an antenna fall off. That would, as you know, would be really, really bad. So when they're carrying an antenna, they only move about 1 to 2 miles per hour, which is about 1.5 to a little over 3 kilometers per hour for safety purposes. And we also don't move our antennas if the wind speeds are above 20 miles per hour or 32 kilometers per hour. And again, we wouldn't want the wind to potentially risk tipping an antenna. And so the nice thing too about this is that even as we move our antennas, we're still able to observe. So out at our site, we have what's called the 3 antenna rule. So out of the 27 operational antennas, not counting the 28th one in the barn, we can have up to 3 of those that we're not using at any given time. Maybe our 2 transporters are moving 2 of them. Maybe we've got one that's having a bad day, and so we're not using it. As long as we have at least 24 of them up and running, we're able to get enough data to keep our scientists happy. But of course, the more of them that we have running, the better. So if we have all 27 up and working, that's our best case scenario. So now I'll pass it over to Summer again, and she will show you a video that talks a little bit more about our transporters.
Straightforward. You see the flat deck on there. The transporter moves down the rails, slides underneath the antenna. The antenna is then unbolted from the 3 concrete piers on which it normally sits. The transporter is raised up on hydraulic jacks, lifting the antenna up about 6 inches, enough to clear the bolts. and the transporter then backs up and takes the antenna to the main line. Now, the way the antenna transporter turns a corner is quite unusual for a rail vehicle. The engineers invented this right-angled turning system, which works in the following way. The transporter moves over the main line, and this is the main line heading down, say, towards the center of the array. It's a double track. The transporter trucks are each over the 4 intersections of the 2 double tracks. A hydraulic jack lifts up one side of the transporter 3 or 4 inches, just enough to clear the flanges of the 12 wheels on one side. The 2 trucks of 6 wheels each on that one side are then rotated by 90 degrees and put back down again. The other side of the transporter is then raised 2 or 3 inches. The other 2 trucks are rotated 90 degrees, and the whole assembly rolls off in a 90-degree different direction. So the
Awesome. Yes, these videos are a little long. So, and a lot of the rest of this video just talks about some stuff that I've already mentioned. So thank you, Summer. Now we'll come back to our slides here. And so now talking a little bit more about the antennas themselves and how they work. So the VLA antennas house a total of 10 receivers. We have 8 main ones that are kept near the center of the dish and 2 additional receivers located in the subreflector, which is this guy up here. And the VLA mainly observes at frequencies between 1 to 50 gigahertz. So if you don't know too much about radios and frequencies, so 1 gigahertz frequency means that since light moves in waves, then a 1 gigahertz frequency is a 30 centimeter long wave, and 50 gigahertz is 6 millimeter long wave. And we can go higher or lower than that for certain observations. That's just the typical range that we operate in. And so that 1 to 50 gigahertz range is divided into these 8 receivers that you see here in the middle, each of which is used for observing different sets of frequencies within that range. And we call those frequency bands. And so when astronomers are asking to use the VLA, they'll specify which band or multiple bands they want to use. And this subreflector here is asymmetrical, so it can turn itself, and it will turn so that the light that is bouncing off the dish up to the top of the subreflector will go to the receiver that the astronomers have specified. And we have to keep these receivers very cold, because otherwise they'll be able to detect or receive their own body heat, so to speak, which would interfere with the signals that we're trying to look at from space. And so from the bottoms of the receivers, the vertex rooms of the antennas, which are kind of located sort of in this range of the antenna down here, they have, this is where we use liquid helium to cryogenically cool them. And we keep them cooled all the way down to 15 Kelvin, which is just 15 degrees above absolute zero, the coldest possible temperature. And so now we'll go to another video that talks a little bit more about these receivers.
I've done that so many times, it's second nature. So this is a 25-meter paraboloid, and the paraboloid works the same way for all. Radiation comes in from the direction the antenna is pointing, strikes the surface. In this case, it runs up to that subreflector, that conical-shaped, asymmetric subreflector. And from there, the radiation is down in a cone to go in one of the 8 feeds. We change our frequency by rotating the subreflector. So these feeds are not on the optical axis of the antenna, but they're arranged around a ring called the feed ring, and we can illuminate any one of them at a time. So that's the reason why we normally can observe only in one wave band or one receiver band at a time. So the 8 horns that you can see there, they're all different sizes. The larger the size, the longer the wavelength. So the big one is what we call L band, 1 to 2 gigahertz. That's 30 to 15 centimeters radiation. which goes into that horn by appropriate rotation of that subreflector. If we're interested in 2 to 4 gigahertz radiation, then the subreflector is rotated by 180 degrees and the radiation goes down that second largest feed horn called S-band. And so on and so forth with the other 6 receiver bands. By appropriate rotation of the subreflector, the radiation from the direction we're interested in will go down through the horn and into the receivers. Each of these horns is covered with this white window material. This is for weather purposes. It's not necessary for the function of the horn. This is to keep rain and snow and dew, bird droppings, and everything else out of these horns. There's a little bit of loss associated with that, but that's just something you have to accept. The funny inverted shaped objects that are above the smaller horns are all heat lamps. We don't want dew or frost forming on the surfaces, especially at the higher frequencies or the shorter wavelengths. So when the dew point and the temperature are close together and sufficiently low for us to determine that dew is forming, the computer recognizes these combination of conditions, turns on these heat lamps, which warms up the surface and prevents frost and dew from condensing on top of these weather windows.
Great, thanks, Summer. All right, so I've talked a lot so far about like the scientists and astronomers who use the VLA. So who is that? Who can use it? Actually, anybody from any country, even you at home, can theoretically use the VLA. It doesn't cost money to use, and you don't have to be from the US to use it. We have what's called an open skies policy, where as long as the science that you want to use the VLA to do is deemed sufficient and we have time to be able to do that, then you can use it. So you have to write a proposal explaining what you want to look at, what configurations and frequency bands you want to use, and explain the scientific merit or why it would benefit this astronomy community for you to do these observations. And for every hour of observing time that we have to give out, we get about 4 hours worth of proposals. So we do have to pick and choose. And how we make these decisions is that we have a panel of astronomers from many different institutions who've used the VLA before. They know really well like what its strengths and weaknesses are, and they will grade the proposals to prioritize them on whether or not what observations we'll be able to do. So if you get a really high grade for your suggested configuration, that means that you're almost guaranteed, unless there's some kind of major issue with the telescope, to be able to get to do your observation the next time we're in your requested configuration. And if it's rated sort of in between, then that means that when we get to your configuration, if we get through all of the higher rated proposals and we have time to do some of the ones that are more in the middle, then we might be able to get to yours. And a lower grade means that you probably won't be able to use it to observe this time, but you can rewrite and resubmit your proposal again in the future. And different configurations may be more or less in demand at different times as well, depending on what's currently happening in the sky. If there are certain objects that are visible or not visible, or there's some kind of major event happening to look at. So even if you submit a proposal and it's not rated very highly one time, it might be rated higher the next time just based on the demand. And so let's say that you wrote your proposal and you've been granted observing time at the VLA. So at that point, you work with our data analysts and use computer programming to write a code or script for the antennas during your observation that tells them what to do and what to look at, because you want to make sure that your observation will actually work and the antennas aren't just going to be spinning around like crazy or anything like that. And so once that's finished, the script is sent to our operators and they put it in the queue or the collection of the different scripts that we have. And when it's time for your observation to begin, the script will pop up on the screen. It'll start talking to the antennas and they'll turn and point at your object and begin taking data. And the data travels from the antennas via fiber optics, digital cables that run underground to our control building. And that's where our correlator is located, which is the supercomputer that processes this data and combines the data from all the different antennas to simulate one big antenna. Because with especially some of the larger configurations, like we wouldn't be able to build one dish that's 22 miles in diameter. So how these arrays work is that the individual antennas look at the object, and then the correlator combines all of their data together, and they act like one big telescope. And so then once the correlator has finished this process, it will inform the operator, and the operator will send the folks on the proposal, so you and anyone else that you might be working with, an email, and it has a URL or a link that you can click on, and that's where you go to download your data. And so from the time that once you receive your data, it's proprietary. So it's private to you and those on the proposal with you for 1 year. And so you can use this time to make images like the ones that you see here from the data. You can write papers, plan further research. And of course, you can still continue to do all of those things after a year, but 1 year after your observation is complete, it goes into our public archives where anyone can access it. And so let's say that I had written a proposal and my proposal was rated pretty low and I didn't get to use the VLA. What I could do instead is go to these public archives, see if there was a similar or at least somewhat similar project that was already done, and use the data in the public archives for my project. Or another possibility is, let's say I have something I want to do and somebody else has already taken exactly the data that I need in the past. I might not even need to bother with the whole writing a proposal and waiting several months for my observation. I might just be able to go straight to the public archives, get my data right from there, and be able to skip the whole proposal process altogether. And so, as you can probably guess, things have changed over the course of our 40 years of observing. So when the VLA was built in 1980, it was a state-of-the-art telescope. But as you all know, technology continues to get better and better. So by the time we reached the 1990s, the VLA was beginning to fall behind technologically. And in late 2001, we started a project to upgrade the VLA, where we gutted all the old technology inside the antennas and replaced it with newer stuff. And we replaced our correlator with a more powerful version, and we went digital. So we used to have an analog version of carrying the data from the antennas to our computers, but that was when we replaced the analog with those fiber optic cables that we have now. And it took us a little over 10 years to complete this upgrade process. And this was completed in 2012, and it's now a 10 times more powerful telescope, once again, cutting edge. And we slightly renamed it as the Carl G. Jansky Very Large Array. So if you ever see it called the JVLA for Jansky, or it's sometimes also known as the EVLA for Expanded Very Large Array, but that just means that it's specifically referring to our new and improved version of the telescope. And so the way that we handle these observations with the scientists and astronomers that we work with naturally has changed over time too. And so when we first built the VLA, we had what we called a fixed scheduling method. So if you were granted time on the VLA, you would be given a set date and time, or multiple dates and times, depending on how long your observations would be, for when that would happen. And it used to be that the only computers that were capable of working with the VLA analog data were located on site, so out at the VLA. And so we used to have astronomers who would come out to stay at the VLA when their data was being taken. And when the observations were finished, we used to have dorm buildings on site where scientists could stay while they were doing their work. But we eventually figured out that the VLA would be more efficient if we had greater flexibility for our observing schedules based on weather conditions. So imagine that you had a higher frequency observation, which requires more clear skies. You were given a set date and time, you get out to the VLA, and then there's a huge slew of thunderstorms during that whole week. Well, that might mess with the data that you get, and it's not nearly as high quality as it needs to be for the work that you're doing. And so in order to avoid that and avoid diminishing the quality of the data, we now use what's known as dynamic scheduling, where our computers have a whole process that they use to decide based on the current humidity and like the weather situations and what's going on right now. Out of the different scripts that we have in the queue, these ones are the best ones to do. So pick from some of these. And so that means that if you've been granted time to use the VLA, you don't know when exactly this observation is going to happen. So during that 4 or 3 or 5 month period that we're in that configuration, you might know, okay, it's going to happen sometime in there, but we don't know exactly when. And then when we upgraded to the Jansky VLA and the new 10s with our greatly improved technology, now astronomers can work on the data from the digital data from anywhere in the world. So you could be on the other side of the planet in your pajamas, theoretically, working with VLA data. And so that means that astronomers don't need to come to the VLA site anymore to work with it. And so once the dorms were no longer necessary, we tore them down about a decade ago. But we do still have some of the buildings from that era out there that are used for other purposes. And so we're already starting to think about what we want the future to look like when the current version of the VLA becomes outdated as well. And so our hope for that is the next generation, or NG VLA, which will consist of antennas smaller than our current ones, about 18 meters or 59 feet in diameter. But we would have over 200 of them spread throughout New Mexico and neighboring states to create a much more powerful telescope even than our current one. And so we haven't decided for sure what the exactly what the spread will look like, but this is our best idea currently. So the picture that you see here on the lower right shows the most zoomed in version. So this is what the center of our NG-VLA array would look like. And then as you spread out a little bit more, this is what that kind of the center, but from the center, this is what it looks like from there. And then when you get onto a much larger scale, then eventually you can see some of the antennas would be in Texas and Arizona and even a little bit into Mexico. And so our hope, we need to get the money to do this. So far we've received funding to continue researching and planning for the NG-VLA, and money to build a prototype antenna too, which is really exciting. It would take about a decade to build. So if we can get the funding, our current hope is that we could start building in the mid to late 20s and complete the project by the mid to late 30s. All right, and so now I'd like to welcome our first guest speaker today. Our operator for the day is Hannah Brower.
Hannah, go ahead and turn on your camera. And Faith, you can stop slide sharing.
Right, here we go.
Can you see me?
Yes.
Hey, Hannah.
Hi, how's it going?
Great, thanks so much for being here today.
Yeah, no, thanks for having me. It's always a pleasure.
And so to give a bit of an introduction to just our VLA operators and what they do and the basics of how the job works. So they act as the site managers for the VLA when they're out there. So they're definitely VIPs. During the weekdays, we have our maintenance staff who works on the antennas. and they have to coordinate with the operators before and during and after their work many times. And the operators also monitor weather conditions, and they keep track of other potential hazards at the site, such as if there's wildlife located in places where maybe it shouldn't be. They are in contact with the scientists about the data that they're taking. And they also coordinate with our security, with the guards that we have on site. And so we do have operators on site 24/7, 363 days a year, or 364 days if it's a leap year. And so everybody gets Thanksgiving and Christmas off when they shut down the site. So yay for that. And so the operators come from our building here, our Science Operations Center here in Socorro, and then they drive out to the VLA site, and that takes about an hour. And then they work out at the VLA for 8-hour shifts. There's the day shift of 8 a.m. to 4 p.m., an evening shift of 4 p.m. to midnight, and a graveyard shift of midnight to 8 a.m. And then they use their staff vehicles to get out there. And then once they work there for those 8 hours, then it takes them another hour to drive back. And so they work 10 hours a day, 4 days a week. And so, Hannah, in addition to that brief introduction there, do you have, like, what else do you have to tell us? Like, what's some interesting stuff about what you do out at the site, or things that happen out there regularly?
Oh, all sorts of stuff. It's quite a fun job. I mean, most of the time you're just kind of sitting there babysitting telescopes, which I know in and of itself is quite fun. And sometimes you see like wildlife getting into gates that surround telescopes. You never know. But it's interesting just being part of the science that way, because most of the time you don't really know automatically what you're observing, because everything is in those proposals format. And then what we see as operators is usually in binary, so just ones and zeros basically. So once in a while you'll look up the proposal and you'll be like, oh, okay, I'm looking at a supernova that was recently discovered. That is amazing. So it's definitely got its perks there. Yeah, it's quite a fun job. Yeah.
Yeah. And so what's the trickiest observation that you've been involved with, and like what's made it tricky?
I'd say probably observations that are coordinated with other telescopes like Hubble or the VLBA telescopes, or both, or something else that's coordinated like that. Those are usually the trickiest, I would say, because you have to coordinate with so many more people. And also we don't always see the data like we normally do for those observations. So when things go wrong, you don't notice it automatically, or someone calls you and says, hey, why is there a hole in the data? And you look outside and the telescope's not working. So that's not always the easiest thing, for sure.
Yeah, it sounds like in general too, there's like a good amount of calling people, sometimes not even at the most optimal times, right?
Oh, definitely not. It's always pretty sad when you have to call someone at 2 or 3 a.m. because the telescope is broken. So one of the motors have quit or something like that has happened, and you have to call them because it's not safe for the telescope to remain in that position. So that's always probably, I would say that's one of the hardest parts of the job too. Yeah. It's waking people up.
Yeah. Sometimes it's necessary, but yeah, it's never what anybody really wants to do.
No, but that's part of the job.
Yeah.
And the technicians know that too. So they have us on their emergency wake up list. And then we call them and say, hey, can you come out? And they'll be there in 40 minutes or something like that. And we just have to wait and hope that nothing else breaks.
Yeah. Also, it's definitely the kind of thing, right, where it can ebb and flow in terms of like stuff that you have happening out there.
Yeah, usually everything just happens all at once within like 10 minutes, and then the rest of the shift we'll just be kind of sitting there being like, okay, everything's fine. And then all of a sudden something breaks or a power glitch happens and all the antennas lose power. Power glitches are absolutely the worst, I will say, because here at home, we think, okay, we lost power. But over there, okay, that means someone's going to lose data. The correlator might run out of power, or some of the cryogenic units that are keeping all the receivers cold might quit, and then all sorts of number of things you have to worry about just from a 2-second power glitch. So it's quite a lot for sure.
Yeah, definitely. Oh, and one thing that our audience members always want to know about our operators is like, what's your background? Like, what kind of background? Is there certain requirements to be an operator? Like, and your specific background and just the background of operators in general.
Oh yeah, and we're actually quite varied too. Quite a few of my coworkers do not have any degree related to astronomy or physics. They have degrees in like computing or engineering or public speaking or even drama or something like that. And I'm kind of like the rare exception. I do have an astronomy and physics degree, so I think I and maybe one other or two other operators actually have that. Well, mostly we just need to have some form of experience operating a telescope, whether it's in radio, which is actually fairly rare to my understanding, or optical. I had no radio experience before this job, absolutely not. And I was still hired, so it's actually quite an open job. Anyone with time management, some sort of background in computers and astronomy, just vague background in astronomy even, you can do this job. But you have to be willing to work very odd hours, that's for sure, and also very long hours. I think that's probably the hardest part of it.
Yeah, and from what I understand, if I remember correctly, there are 7 VLA operators, right? And there is one gentleman who only does midnight shifts. So that's nice because 4 out of the 7 midnight shifts every week are covered by him, which I guess makes it a little easier on you guys, but somebody still has to do the rest of the midnights every week.
We definitely love him. he's been there the longest too. He's the oldest operator that we've had. He's been there for over 20-30 years, I think.
Wow.
So yeah, he enjoys his midnight shifts, only does them, and we love him for it. For
Yes.
sure. They're not too bad. Yeah.
And then the rest of you kind of like rotate, right, between the days and the evenings. So everybody kind of does everything.
Yes, we generally, now that there is 7 of us, some of us can kind of pick and choose which ones we like. But every week is typically a little different, either a evening shift or a day shift, or sometimes a midnight shift because Sam needs his sleep once in a while as it goes. And we do get those 3 days off, so that works pretty well.
Yeah.
That dark.
Yeah, that does sound really nice. Yeah, so also feel free to, everyone in the audience, feel free to keep submitting questions for Hannah. So I'm taking from the Q&A as well. So we have a question here. How quickly does the observatory react to any unexpected astronomical event that requires fast coordinated observation, like a supernova or something?
Very quickly, actually. Well, we have a special email and proposal type of block for those. It's like it's called 2SOC. I'm not entirely sure what that means in its full format, but it is if some sort of supernova event or something big happens that requires immediate observation, it immediately contacts the schedulers, the data analysis, and anyone that's involved with submitting the proposal so that we can get it, will immediately put it into our schedule and format it so that it'll run properly. And then we'll be involved and we'll talk and communicate with it. So typically I've seen these, I'd say within about 2 hours sometimes, if it's pretty quick. Yeah.
Yeah, that's great. And I guess after 40 years of doing this kind of stuff, that makes it easier to like become more of a well-oiled machine, learn like best practices for that sort of thing too. So
yeah. So it's a pretty good, smooth process most of the time. Sometimes it definitely doesn't work out, especially since the internet connection isn't always the greatest. And we can't use cell phones, we can't use microwaves or anything at the site like that. So we do have a limited network, but it is a very strong network. So we get it done somehow.
yeah. And so another question that another question that we have here is, can you observe during thunderstorms?
Yes, we can. We'll typically switch on to our backup generator, which most of the time works. And that way we don't have to worry about, because otherwise our electricity comes from Socorro, so it's about an hour away. The backup generator is definitely quite needed in those cases, because often lightning will sometimes strike a electricity pole or something like that, and then we'll lose electricity and have to be on generator, things like that. But mostly thunderstorms will only limit the higher frequencies, so we are still able to observe in, say, L and S band, those big receivers that you saw in the video. Those are still very able to get science, which is good.
Yeah, and sometimes from what I understand, lightning has struck antennas themselves too, but that you can still continue to observe even through that. So
yeah, so sometimes it doesn't even affect the antennas, surprisingly. I've seen lightning strike an antenna and it still keeps tracking. So as it is, I believe they're all grounded, and I know that the control building is also grounded, which is very good. That way we don't have to worry about lightning affecting our correlator, which should never ever be shut down. It's our special supercomputer, and that is very well protected. Yeah.
awesome.
That's
Any
great,
other
Hannah.
questions? Yeah.
I think we might bring you on at the end, just because we never know what kind of questions we're going to get over the next hour. I'm sure that some of them will still be operator specific. I'd also like to follow up on your lightning comment by letting everybody know if they would like to buy a Bon Jovi album. It comes with a photo of the VLA being struck by lightning.
That is very true.
On the
Apparently
cover.
there's even a Puma commercial that you can see the VLA in that I've heard of. So
Yes, there's been several ad campaigns, pop culture things, in addition to the very famous one.
Avengers. Of course, the Avengers. If you ever watched the first Avenger movie, when
Exactly.
everything's collapsing, where that's the VLA. Yeah. So it's not just contact. We actually are movie famous.
I know.
Yeah.
Look at us. Well, thank you so much, Hannah. Hang tight, and hope we'll see you again before the end of today. And thank you so much, Faith, for that fantastic introduction to the VLA. There's just so many amazing things about it that I never get sick of hearing anybody talk about them. So
yeah, and once you get started talking about it, it's like, this is so cool. I just want to share it with everybody. So
exactly. Especially since we can't go out there right now because we're still shut down. So we miss our BFFs.
We do. Sad but true.
Okay, so I'd like to bring on our 4 guest speakers today. So if Amy and Kevin and Shami and Ron would unmute themselves and start their videos, that would be great. Hello. Hi, everyone. You all are so incredibly amazing and accomplished that I hope I'm not going to embarrass you, but I do want to read some of your bio highlights. So I just want people to know exactly who we've got joining us today. Starting with Amy. Amy Barger is the Henrietta Leavitt Professor of Astronomy at the University of Wisconsin-Madison. And everyone should go look up Henrietta Leavitt because she's awesome. And Amy got her PhD from King's College at the University of Cambridge and did her postdoctoral work at the Institute for Astronomy at the University of Hawaii, as photoed behind her. You're coming to us live from Hawaii, is that correct?
That's correct.
And Amy has made pioneering discoveries of distant galaxies and supermassive black holes through observations at multiple wavelengths across the electromagnetic spectrum. And today we're going to actually ask her to focus and pick just one of the radio. So welcome, Amy.
Thank you.
Next, we have Shami Chatterjee. He is a principal research scientist at the Cornell Center for Astrophysics and Planetary Science and the Carl Sagan Institute. And after he got his PhD from Cornell, he was a Jansky postdoctoral fellow here at NRAO and the VLA. He currently studies neutron stars, works on the forefront efforts to use them to build low-frequency gravitational wave detectors, and has been in hot pursuit of fast radio bursts, FRBs, that you will hear much more about later. They are mysterious flashes of radio waves coming from billions of light years away. And his work localizing one fast radio burst in particular and identifying its host galaxy made the cover of Nature and was covered by New York Times and Washington Post, and even his hometown newspaper in India. Welcome, Shami. And next we have Ron Eckers. Ron is I don't know actually how you say the acronym. Do you pronounce it Cicero, or do I just read it all out?
CSIRO.
CSIRO, the Commonwealth Scientific and Industrial Research Organization in Australia, and he's an adjunct professor at Curtin University in Perth. And he has had a very distinguished international career in radio astronomy. He was the first director here of the VLA from 1980 to 1987, after which he returned home to Australia to be the first director of Australia's Telescope National Facility, which operates 4 different radio observatories. And he's been the president of the International Astronomical Union, the world body that represents professional astronomers, and received multiple awards, including the Grote-Reber Medal for Innovations and Contributions to Radio Astronomy. So we're very excited to have you here, Ron. Ron, you are in Australia right now, so we are especially grateful for this early hour that you are joining us.
Oh, it's been very interesting to remind me again of the VLA, which of course I knew very well.
And lastly, we have Kevin Marvel, who is the executive officer for the American Astronomical Society, which is the professional society of astronomers here in the US, and was a summer student at the VLA in 1988 while doing his undergraduate degree at the University of Arizona. His experience at NRAO is what confirmed his interest in radio astronomy. He went on to do graduate school at New Mexico State University and came back to NRAO to complete PhD research on one of our other facilities that Faith mentioned at the very beginning, the Very Long Baseline Array. And what's really cool in his time at AAS, which is what we call the American Astronomical Society, he helped establish a formal public policy program and has spent many years actively lobbying policymakers to support astronomy and other sciences while educating and involving the astronomy community in the effort. And I've benefited from that, Kevin, because I've done the congressional visit stay and it was quite the experience. So thank you all for joining us. I definitely want to encourage all of you to, react to each other and jump in and add to each other's answers. But chronologically, I would really love to start with Ron being the director, the very first director of the VLA. And I want to know what it was like. Was the director job just advertised somewhere and you put in a proposal for it? Or were you handpicked? How did that come to be?
I think I was handpicked because starting back in the mid-70s, there was an external advisory committee during the period the VLA was being constructed. At that time, I was living in the Netherlands, and that was the biggest radio telescope before the VLA was built. So I knew how a synthesis telescope worked. I had hands-on experience for a decade with the biggest telescope before the VLA. So I think for that reason, I was asked if I would be interested in coming to the USA. I have one American child and I had lived in the USA before, so I was quite familiar with the possibility. And of course, having the world's biggest telescope is too exciting an opportunity to pass up. I think that wouldn't happen these days, but back then, no, I don't think there was an advertisement for the job.
And how was the VLA received by the community when it first came online and began operating? Was it in demand right away, or did it take a while to drum up the demand that we have for time on it now?
It took a little while to drum it up, but the NRAO had already been running 2 other radio telescopes in Green Bank in particular. And the NRAO had set a world standard of demonstrating how you can run what's called the National Observatory with this open skies policy. So it was known throughout the world that if you had a really good idea that required a radio observation, then you could work with NRAO to do that. So there was an instant international community. But what was missing were people with experience with these multiple telescope arrays. Most astronomers had used optical telescopes or perhaps single dishes. So it took a few years, maybe 5 years, before people got used to this way of observing.
And how was
and in fact, in the, I think it was already in about the 2nd year, we realized that we had an educational role to play. And Summer, if I remember right, your introduction to the VLA was something called one of the VLA workshops, which were run every year.
It was
we started that quite specifically to train and give people insights into how these beautiful telescopes work, because the principles are themselves very interesting, and it's a very flexible way of imaging the sky.
Shami, did you want to jump in?
Yeah, I want to quickly jump in and
Absolutely.
highlight something that Ron mentioned there, which is the open skies thing. That's very, very different from how most other observatories work. For example, with optical telescopes, you really have to be at the university that runs that big optical telescope to be able to get time on it. Whereas radio astronomy, for various extremely interesting sociological reasons, has always had this tradition of everyone submits proposals and the best science gets done at the observatory, which has made them enormously productive as well. So that's something that Ron mentioned that I thought I'd highlight for everyone. It's really, really interesting.
No, I absolutely appreciate that, because I do think that's one of the coolest things about the VLA, and I love telling people that that's how it works here. And so, Ron, what was your day-to-day life like at the site those early years?
Well, I brought my family from the Netherlands, and perhaps the biggest geographic contrast almost you could get is between living in the Netherlands and living in New Mexico.
Right.
I remember my children when they arrived looking at a map, or perhaps before we arrived, and we had just spent a sabbatical in Australia, and they like swimming and love beaches. And about a 10-year-old son says, "Dad, did you try and find the place where every beach was the furthest possible distance from where we are?" And Socorro, New Mexico must be close to having that. But we, of course, we loved New Mexico. We became addicted to Mexican food and really liked the way of life here. So I think it was a very easy transition and super exciting. It was a new observatory, a very young group of incredibly enthusiastic people. It was a great experience.
And did you have summer students starting right away?
Well, the summer student program, maybe not right away, but I remember it very well. And one of the things which may have been innovative, which we did and which I insisted on, was that the summer students who came would do at least one project of their own. That is, not do something that some senior astronomer had told them to do, but come up with their own idea. And over time, that program has sometimes been hugely successful because there have been cases where the summer students have made observations which no professional astronomer had thought of doing, and even had publications. So that was very successful. And of course, it's a great opportunity to get some firsthand experience.
Kevin, was that your experience? Did you get to choose your summer project and then also participate on some existing ones that higher ups were doing?
Sure. So I think I started a couple of years after Ron had left as director and Miller Goss was director. And our group of summer students that came in had sort of two sets of projects. We had a project that we worked on closely with our advisor, who in my case was Miller Goss, and that represented much of what we did. We also had sort of an education program during the summer so that we had classes with some of the scientists of the VLA, and they walked us through how radio astronomy worked and the physics behind it, the astrophysics, which was really interesting. We got to participate in the colloquium talks, attended those every week, and the roulette lunches where people could show up with one piece of paper and talk about a new result that they had. That was always exciting. And then as a group, we got to have 4 hours of observing time. As I remember, it was somewhere between midnight and early hours of July 4th for some reason. And we actually opted to observe the galactic center looking for water and OH masers. And so we managed to get those observations, and a few of us worked on them during the rest of the time during the summer and got the work done. We didn't end up thinking that we had anything publishable at the end of the day, but it was really exciting to be able to stand out there on the plains of San Agustin in the middle of a New Mexico night, watching the telescopes move to your commands, which you had typed into the computer earlier in the week. And then the next day have the data that the telescope had produced for you. So it was a really great learning experience. And I think they run it similarly today. And many of the scientists that end up becoming career workers at the NRAO and also working in the broader field have gone through that summer program. So it's been a really great pipeline to generate great scientists, I think.
Can you explain just briefly what a maser is?
Yeah, sure. So a maser is similar to a laser. So light amplification by stimulated emission of radiation. In the maser case, it's microwaves. So it ends up that certain situations in nature can be set up so that gas can amplify background radiation and make extremely bright, concentrated emission that can be picked up by the array. And I studied that for my dissertation. There ends up being masers that can move around in the atmospheres of evolved stars. And you can watch them very, very carefully over time and see that they move, which is spectacularly exciting because most of the time in astronomy, you don't see anything moving, or not too much anyway. And so having masers move, you can then model how the gas is moving around the star and how they're expanding. And it's a fascinating area of research. I see Ron has his hand up.
Yeah, go for it, Ron.
Kevin reminded me that my most exciting day in my career was related to the Galactic Center. So if you liked summer, I don't know if it's practical and I could share the screen, I could show you the image, which was the highlight of my entire career, in fact. Is
yes,
that okay?
please.
All right.
Yeah, you should have privileges.
Share the screen here. Screen. So I'm assuming you can see a beautiful picture of the Milky Way. It's over optical telescope in Chile. And as Kevin just said, one of his first observations was looking at the center of our galaxy. Now, if you look at the Milky Way, you see there's this dark band running through the middle, and that's the dust. And that means that you can't see what's actually in our galactic center. If you can see my cursor, it's this region here, directly overhead, because this is Chile at minus 30 degrees. Now, when radio astronomy started, which was only after the end of the Second World War, and here in 1953 is a telescope in Australia that was built. As you can probably see, it's just a hole dug in the ground and it's actually covered with chicken mesh. So that was an early radio telescope. But radio waves can see through the dust, and so they could see the center of the galaxy. So the people who built this telescope, and by the way, these are the same people, John Bolton in particular, Joe Pawsey, who came to the US and initiated the concepts which resulted in the VLA, because not only the astronomers come from all over the world, but engineers have also circulated throughout the world in this business. So this is the image which they made with that telescope. So a bunch of contour maps, but you see right in the center, there's a very bright bit. So we knew there was something bright in the center of the galaxy. So it was pretty obvious once we got the VLA now is not just a hole in the ground telescope, it's this whole array, and we could make an image for the first time. So I put in a proposal to look in the center of our galaxy, an obvious thing to do. And on the TV screen, this is what I saw. And it suddenly struck me that what an incredible privilege to be the first person on Earth to actually see the center of our galaxy. So it is incredibly exciting and humbling all at the same time. And what we saw was quite amazing. We see this swirling spiral-shaped thing, and the center of our galaxy is in this region here. And this is gas which is swirling around the black hole in the center of the galaxy. About 20 years later, that's what a much more refined image looks like. Over on the left, young stars being born, they become supernovae, which makes the big rings. But right there is a black hole and the gas is swirling around it. So I just thought I would try and convey to you how incredibly exciting and privileged we are to be able to see some things in the universe for the first time.
Absolutely. This second photo is made with the VLA as well, or second image?
Yes. This is an image that was made by Neil Killeen using a supercomputer to calculate the large image. That was about 15 years after the first one I showed you, just due to the improved quality of the imaging.
Yeah, those are beautiful, Ron. Thanks so much for sharing. And I want to clarify for the audience that the colors there are kind of false colors, just chosen to show a bit of a spectrum, to show more or less brightness of the emission that's coming from there. So in that green and yellow, I think green was less emission and yellow was the bright.
Yes,
those were great. Kevin, I believe, well, just from some Googling, that you were also looking at a radio galaxy or a supernova remnant with Miller.
That's right. So I actually had to go back and look up the paper that was subsequently published to remind myself of what we had done. But I only helped in the in the very beginning of the imaging processing. Basically, Miller had some data from the Westerbork radio telescope, and looking at 3C58, which is a supernova remnant, gives off continuum radiation. So he was using it as a sort of a background light source to study neutral hydrogen between us and the supernova remnant. So he was so what we actually did was we used spectral line observations to be able to measure the hydrogen gas between us and the supernova remnant. And the cool thing about that whole project, which was ultimately finished by Doug Roberts, who's a subsequent student who worked with Miller and now works in public outreach in astronomy and science museums, was that we were able to figure out the distance to the source at some level, which I found absolutely amazing. And so that had impact on my choice of my PhD dissertation, because I think measuring distances in astronomy is the most interesting and exciting thing that you can work on, a personal take. It ends up being extremely hard to measure distances in space. There's no ruler you can just lay down. So you have to come up with all sorts of tricks and have a good understanding of the objects you're looking at to be able to make estimates of the distances to things. And I just thought pinning down distances was something really interesting and intriguing.
Yeah. Amy, you have to pin down some distances, don't you? Some really big distances. Because you're looking, you know, I say high redshift is our astronomy term, but that just means really, really, really far away back towards the, you know, beginning of the universe.
That's always the most challenging thing in astronomy, is trying to get distances. And for my research, so I'm going to violate your rule a little bit, I have to introduce the millimeter observations, as that's how I got started in radio astronomy. And so it's a millimeter wavelength. So this is like 200 microns and up to about a millimeter. You want to find galaxies that are obscured or cocooned in dust. And there was this new instrument on the James Clerk Maxwell telescope in Hawaii called SCUBA, even though you had to have really dry conditions to observe with it. So the name was a bit of a misnomer. I always think of scuba diving, where it's very wet. But this instrument, for the first time, gave us the sensitivity and area coverage to discover this extremely luminous, massively star-forming galaxies at great distances. And so it was super exciting to be involved with those early observations. This was in the late 90s. But the problem with the sublunar observations is it was a single dish. We didn't have a nice array of telescopes. And so the resolution was very poor, which meant rather than seeing, say, a Hubble Space Telescope image of like the Hubble deep field with thousands of galaxies, you would see like 5 blobs. and it was roughly the same area as the Hubble Space Telescope image. And so the challenge was trying to identify any counterparts to those blobs in particular, so you could put a slit on it and try to get a redshift measurement from a ground-based optical telescope. And so we really became very dependent on VLA observations. So a good collaborator of mine, Fraser Owen from NRAO, had obtained really deep image of the field we were interested in, and at 1.4 gigahertz or 20 centimeters with the VLA. And so we were able to use that image, which has sub-arc second resolution, to try to pinpoint the positions of the sublunar sources. And the reason it works is that both the submillimeter emission and the radio emission was due to massive stars forming. So young, hot stars that had formed and were emitting this light at UV optical wavelengths, but it was getting absorbed by these little dust particles, these smoke-like dust particles. And that dust was re-radiating it at these longer wavelengths. And so that's why we were able to observe them at the submillimeter, but not see them very well at UV optical wavelengths. So the radio is great because the dust grains are so much smaller in comparison to the wavelengths, at radio wavelengths, that the radio is unaffected by the dust.
Right. So similar then to like the photos, obviously they're much farther away, so you're not going to get that detail of the galactic center, but the radio can see through the dust that would be obscuring if you were looking at the higher wavelengths.
Yes, it's not a very impressive image compared to what Ron showed us. A 20 centimeter continuum image is, just little dots here and there, but it's incredibly powerful.
Yeah, because those dots are a galaxy at some incredible distance. Like, I still think that's impressive just because it's what the dot means.
Yes, exactly.
And so in addition to the galaxies, you also do research with supermassive black holes.
Yes.
Are those like in those galaxies? So you're looking at the activity of those at those long distances?
That's right. And so the submillimeter, we think, is mostly picking up star-forming galaxies, but the radio picks up both star-forming galaxies and supermassive black holes. So you do need to differentiate between the two. And one way to do that is to use a worldwide telescope interferometer like the VLBI to try to find how compact the source is. Because if it's extremely compact, then it's definitely going to be a supermassive black hole. where it'd be more extended if it was, star formation across the galaxy.
Yeah, and for the audience, the VLBI is referring to sort of a larger network. So the VLA is here on the plains of St. Augustine, but you can also link up dishes that are across much wider distances. And as Faith mentioned, the whole big is small, small is big. The bigger the spread in those dishes, the smaller that you can resolve something on the sky. So if you want to get really pinpoint, you get the big guns out. Speaking of pinpointing, Shami, I want to talk to you about how, first of all, fast radio bursts I know are a very new, hot field. And I think a lot of people aren't necessarily familiar with them. So can you give like the fast FRB 101 for us?
Sure. In 3 sentences, I guess, FRBs are these mysterious radio flashes that are going off all over the sky. And the problem with FRBs is that our radio telescopes, or any telescopes actually, are only looking at a very small patch of sky at any given point of time. And because these radio flashes last just milliseconds, if you're not looking at exactly the right place at exactly the right time, you're never going to see one.
Right.
And so even though so now because we've surveyed the sky for so long, we've seen a handful of these FRBs. As of last week, there are 600 of them published, of which 500 come from this one Canadian radio telescope called CHIME, because it is optimized for finding FRBs. So before it came online, it was only about 100 of these fast radio bursts that had been found. But we can infer that every single day, there's about 5,000 of these popping off all over the sky like flash bulbs. And if you're not looking at the right place at the right time, you're just not going to see it. And so I started off working on neutron stars, radio pulsars, and in particular, something that Amy said about measuring their distances. I worked throughout my graduate school career on measuring the distances to these neutron stars so that we could do a whole bunch of really interesting things with them going forward. But the way these neutron star pulses work is it's a radio pulse, but as that radio pulse travels through the vacuum of space, space is not quite a perfect vacuum. It's almost a perfect vacuum, but it's not quite a perfect vacuum. And that tiny bit of stuff means that higher frequency signals travel a little bit faster and lower frequency signals travel a little bit slower. And so when we receive the pulse, because of all the stuff in our galaxy, it's sort of swept from high frequencies to low frequencies. And there's this sweep, and that sweep tells you how much stuff there was between you and the neutron star that produced it in our galaxy, right? Because the further away it is, the more stuff in our galaxy it will go through, and the more this sweep will be. So when these fast radio bursts turned up, they were found in the same way that we find radio pulsar signals, except that the sweep was too much. There was too much sweep for the direction they were coming from. And we were like, well, if they're coming from within our galaxy, we run out of stuff. There shouldn't be this much sweep in the signal. And so that's how we figured out that they were actually coming from beyond our galaxy. And so beyond our galaxy, you hit something called the intergalactic medium. Mm-hmm. And if you think that the interstellar medium in our galaxy is a pretty good vacuum, the intergalactic medium is orders of magnitude emptier than that. And so that means that to get some sweep in the signal, you have to go orders of magnitude further away. And so now we realize that these fast radio bursts are coming from billions of light years away instead of the thousands of light years within our galaxy. They're actually coming from billions of light years away. And so it's pretty remarkable stuff. Because the other thing that happens is if we are actually seeing something from that far away, that means that where it's emitted, it has to be incredibly bright. And so it has to have an incredible amount of energy when it's emitted.
I just pulled up your Nature cover.
Yeah, the reason I'm very proud of this is the first time the VLA, the telescope itself, has appeared on the cover of Nature. There have been other VLA results on the cover of Nature, but never the actual image of the telescope. So this is very cool for the observatory.
Exactly.
Yeah.
And Shami, you were also a postdoctoral researcher here in Socorro.
Yeah, before I was a postdoc, I spent a year in Socorro as a graduate student, and I was working with Miller Goss, and we were starting to measure distances to pulsars. And then after I got my PhD, I was a Jansky Fellow, and I spent a year in Socorro and 2 years at Harvard in Boston. So
Amy,
so I've lived in Socorro on 2 separate occasions for 1 year at a time.
I think this means that we need to get Amy working with Miller because the other 3 of you have known Miller and worked with him. So
yes,
we need to go for the clean sweep. For those of you, I think Ron mentioned it briefly that Miller took over as director of the VLA after Ron, and he is still an emeritus here in Socorro. And I'm going to go hang out with him and his wife after this tour is over. Kevin, I saw you answering a question that was already submitted, but for the rest of the audience, can you tell us a bit more about the background, your virtual background? Oh, you're muted. You're muted.
Yeah, sure, thanks. So the VLA played a central part in my career, frankly, and got me interested in astronomy and confirmed that I could pursue astronomy, and I've enjoyed that path. But I've always loved the VLA. I've always loved representations of it and images of it. And this picture was painted by a college roommate of mine who went on to become an elementary school education specialist. He lives in Albuquerque, and he's taken up painting as he's gotten closer to his retirement age. And he's been commissioned by me to make 4 such pictures. This is one in each configuration. I'll get out of the way a little bit like that. And if I can, I have a second one ready to go.
Yeah.
This one.
Oh, the D darn close together in configuration.
Yeah. And the nice thing about it is that he's really captured the colors of New Mexico, which have sort of striking beige and purples and reds. You really, when you see it and look at it closely, you can certainly see those colors. And so that's one of the things I liked about his style, was that he really captured New Mexico well. And he had been doing canyons and mesas and all the standard things. And I said, hey, how about you go down to the VLA and hang out and make some paintings, and we'll get them out there. So he's got 2 done and 2 to go.
Nice. Well, you have to send him over to say hi when he comes back for the next one. And Amy, as Ron mentioned, I think both of us attended the synthesis imaging school workshop. Is that correct? Is that your early connection to the VLA?
I have not attended any of the schools, unfortunately.
No, but you have been out here at some point, haven't you?
I did come out, yes. I did some radio observations out there in the early, I guess it was the early 2000s. And yeah, it was so fascinating to be out there. I was super excited. It was my first time like seeing an array of telescopes. I've subsequently had the privilege of seeing the ALMA array of telescopes, but yeah, the VLA was my first experience, and this is something that everyone should try to do if they can. It's just so cool.
I completely agree. Yeah, Shami.
Yeah, this is something, again, that's different from even today, most optical observing, where thanks to efforts of people like Ron, I guess, the VLA has this very custom end-to-end system where you send in a schedule for what needs to be observed and how it should be observed. And then you basically get back your observations. You get the data files for that. It has its pluses and minuses compared to actually going out to an optical telescope and sitting in the observatory dome and some stuff like that. Used to be, I guess Ron can say more about this, it was the only place that had enough computation power to make those images. So you had to go out to the site. And now that's no longer true, I guess.
Yes, when the VLA started, the computational requirements were really enormous. In fact, when it was proposed, there was no computer that was capable of calculating those images. And the plan had been to use what's called an analog device. The outputs of the VLA antennas will actually modulate a thin film, and you shine a laser on it, and then you image that, and you can get a kind of thing you could photograph. no computers at all. By the time the VLA was finished, it was just possible to compute these images, but these required computers which were much larger than any university organization had. And for about a decade, that was the case. Then slowly, the computer power and the ability to have a computer on your desktop made it possible for everybody to compute the images. I think somebody pointed out the first VLA computer, I think called the DEC 10, was about 1/10 the power of the laptop PC you would have today, but that was the biggest that was available then.
Let me just hop in. During the science conference we had this week, people were showing pictures of their personal data tapes. And in the early days, the VLA had these 9-track data tapes, these big 10-inch wide things. And I looked up, just out of curiosity, they held about 150 megabytes of information per tape. And when I went to the VLBA to do my dissertation, I was using exabyte tapes, which is these little videotapes, which held about 2 gigabytes of information per tape and were about 1/10 of the weight and much easier to use. But it was still, it seemed to me like a huge fraction of my dissertation research time was spent tape managing. I had to manage, 30 or 60 of these tapes. They had to be loaded on and off as we did different data sets and merged and processed. And now, everything's so much better that hard disks can carry these huge amounts of information. I have a 10 terabyte drive sitting on my desk. It's just phenomenal how far things have come. Yeah, what do you have, Shami? You have
This is 2 terabytes.
2 terabytes in a
Yeah,
disk.
it's
Right.
and now we have petabyte archives. It's amazing.
Yeah, it's just crazy.
And so, Kevin, when you were here that very first summer, were you living out at the site?
No, we were the last set of summer students that took the bus out to the site. So we lived in town. We called each other up ahead of when we were selected. We were given each other's names and contact information, and we actually called up on the phone and talked to each other and arranged to rent a house. And we got a house that was about a block away from where the little building was that handled like administrative work for the array. It's now the library at New Mexico Institute of Mining and Technology. But the buses would meet there and we'd all load on, and then you would drive out and you had an hour or so to talk with your friends, talk with the scientists. Some scientists played bridge on the way back in the afternoons from the site. And you got to go out to the site and work there. Over time, the summer students discovered that we could take a later van that went out sort of at 10 in the morning instead of 6 or 7 in the morning, which better met our sleep schedules. So some of us started taking that van out. And one very strong memory I have from that time was we would often be working late in the day, sometimes even on weekends out at the site, again, because that was where the computers were. But there was a difficulty getting food on the weekends, except that we could drive on into a small town called Daddle, which is another 25 miles down the road. And they had this place called the Eagle Guest Ranch, which was just phenomenal. It was very, salt of the earth kind of place. Ranchers would come in there, and they had this special, I think it was a steak dinner that came out, and the steak was so big it sort of went over the edges of the plate, and they put the mashed potatoes in the center of the steak. And then on certain nights they had Mexican food night, and it was just a spectacular time. And the reason those things, I think, come back to me is because the culture of the VLA is really strong. The people that work there are really passionately connected to its mission and purpose, from the person who answers the front desk to the scientists that are working to process the data, to the engineers. And that culture is just amazingly strong and has lasted as different people have come through. Everybody sort of knows the people that were there and who's come later, and they communicate back and forth. And I think that a lot of times people forget that science does get done, but science gets done by people. And so the culture that gets set up and established and is maintained and carried forward for an institution like the VLA, like the National Radio Astronomy Observatory, is fantastically valuable because it's a supportive environment, it's a creative environment, it's a environment where people are all focused on making something happen, which is making great machines produce great science. And that's not trivial to do. And I think it's impressive that the leadership of the organization and the people who have participated over the years have managed to keep that same, spirit and energy going that I was lucky enough to experience at the beginning of my career.
Yeah, very well said. You're reminding me, and in part of this continuous culture and stories being told, going back to your advisor, Miller Goss, his first graduate student was a professor that I ended up working with at Columbia University, Jacqueline Van Gorkum, but he loves to tell stories about when she was out here, she chose to live in Daddle instead of Socorro, so she could get to the VLA sooner and have time on the computers before anybody from Socorro got there.
If you've met Jacqueline, you know why that's a true story. Yeah, she's a very, very energetic and passionate scientist.
And
she's very passionate, but Jacqueline told me a different reason. It meant for the first time in her life, she could practice her violin, making as much noise as she wanted and nobody would complain.
I like that story too.
But speaking of the guest ranch, at some point she had a salad on that menu named after her. And she was apparently referred to as the Dutch girl of Daddle because there was only one Dutch girl in Daddle. So that was very clear
awesome.
that they were referring to.
I hadn't heard that. It's great.
So Amy, when you came here and you were getting data with the VLA, it was still being completely done by the operator, and you'd previously submitted a script. Is that correct?
That's right. That's exactly it. Yeah. So just being out there was more just to make sure that the observations that I wanted were being done. But yeah, I didn't have control over the observations themselves.
But you got to then be in the office that is now in Socorro that didn't exist in the early days, and talk to all the other engineers and researchers who were working with the VLA.
Right. And it was really fun to be there because I don't consider myself a bona fide radio astronomer because I do work in a lot of wavelengths. I haven't really dedicated myself in the way a lot of people have, but the radio astronomers are just so amazing because they are incredibly technical. I mean, they can go out and solve anything, it seems. I mean, when you go out there and you see how complex things are, and they know exactly what to do. I feel like you have to be a black belt kind of engineer to be a radio astronomer. So I've always been super impressed by real radio astronomers.
It is a real interesting mix between, or an intersection between engineering and astronomy and astrophysics.
Yeah, it's funny. There's a lot of radio astronomers, me included. My background is electrical engineering. I was an undergraduate electrical engineer before I became a radio astronomer as a graduate student. And there's a lot of crossover between electrical engineering and radio astronomy.
To some extent, this may be historical because radio astronomy developed as a byproduct of the radar, which was developed in the Second World War. And the first radio astronomers were not astronomers, they were all engineers. And for the first decade, most astronomers did not regard, it was called cosmic noise. It wasn't even called astronomy. And it took about a decade before radio astronomy was accepted as a legitimate part of astronomy. And then engineers started to also use radio waves. This was the first time that any other wavelength was used for astronomy. Now we have, as Amy was mentioning, multi-wavelength astronomers. We can get observations at radio, infrared, ultraviolet, gamma ray, and even gravitational waves.
Yeah, it's the benefit of being a relatively young discipline compared to Galileo inventing the optical telescope. This is still, comparatively speaking, hands-on. We're soon approaching the era, I think, with the next generation of radio telescopes where the astronomers will not be hands-on with the instrument anymore. I mean, when I was, as a graduate student, I've still been to radio observatories where literally there's a cable that's coming out of the back end of the telescope, and you can plug your back end into it and you go. Arecibo was very famous for that. Like, you could bring your stuff in and just plug into the output of this giant telescope, and it was just going to go into your machine. Modern radio telescopes are not like that anymore, and won't be, because it becomes more professional as time goes on. But it's a great time.
Yeah, and I love pointing out to our visitors that it still hasn't even been 100 years. I mean, it's less than 100 years since radio astronomy's been around. And I love the fact that radio astronomy becoming its own thing was what forced people to have to differentiate between optical and radio, because before it was just astronomy and just light.
That is correct. Perhaps a note of historical interest, and one that Miller was one of the people who found, was that when Pawsey became the director of NRAO sadly he died of cancer a few years later, so he didn't stay on, but he's the person who actually introduced the term radio astronomy.
That's great.
And Miller has found the initial documents showing that that was the case.
At least radio astronomy is still using electromagnetic waves. So all the way from radio astronomy through optical, ultraviolet, X-rays, it's all forms of electromagnetic radiation. And now we have this whole new window with gravitational waves, which is just not even electromagnetic waves at all.
And are you doing any work in that area as well, not just on the electromagnetic side of the neutron stars?
Well, so we are building this low frequency gravitational wave detector effectively by doing radio astronomy and timing these pulsars. So we study these pulsars that are spread out throughout our galaxy, and the distances between us and the pulsars are like the two arms of the LIGO gravitational wave detector.
Right.
So the distances between us and the pulsar are like each arm of LIGO. And so that's how we're trying to detect gravitational waves, which are very, very low frequency. So we are in fact looking at gravitational waves that have wavelengths of a light year.
Wow.
Yeah. And so the wave takes a year to go up and down effectively. And in that time, the distance between us and these distant pulsars changes by a few millimeters and back.
That's amazing. One thing I want to make sure that we cover before we say goodbye is the fact that I'm trying to figure out how to share my screen, is a little fun that I know Kevin and some friends of his had during their summer at the VLA. Do you want to start telling the story, Kevin? How did this actually come about?
So it ends up that the summer student program started back at Green Bank before the array was built out in New Mexico. And there had been a tradition, we were informed on one of those long bus rides from Socorro out to the site, that the summer students always did a prank. And so it was incumbent on us as respectable summer students to develop our own prank. So we sat around at a barbecue one evening at the house and tried to come up with pranks. We had a whole list. Some of them were very dangerous, in fact, for us personally and for the instrument. And so we opted for this one, which was that we called into the Albuquerque Journal to place a classified ad selling the array. So we said, must go 28 used 82-foot satellite dishes, HBO, you bet, 25 million new, must leave state, $500 our best offer. And then we gave the phone numbers, the actual office phone numbers of John Spargo and Rick Purley, who you saw in the video earlier. And we published this. Now, we thought we were going to be really sneaky with this, but at the time, the Albuquerque Journal charged people for classified ads somehow through their telephone bill. So the telephone bill at our house was linked to this ad. So whenever the powers that be at the array at that time called to find out who in the heck had managed to publish an ad like this, they quickly identified it was us, because it was in Ed Murphy's name, who was one of my fellow summer students. So anyway, then the next day, a reporter, the ad was yanked because of course the telescopes weren't for sale. Rumor is that at least one person called and said that they wanted to reserve 2 of them, but they needed to get their uncle's F-250 pickup truck. So could we hold them for them? I don't know if that was real or not. But then the next day, after the ad had yanked, some reporter at the Albuquerque Journal thought this was a good human interest story. So he called up and interviewed us, and then we landed on the front page of the New Mexico section of the Albuquerque Journal. And frankly, we got in a little bit of trouble because some folks thought it was pretty funny and some folks thought it was not very respectable. But we know it. 4 of us went on to fairly good careers in astronomy. One person ended up as the department chair at Caltech Astronomy. One person is currently working at University of Virginia. The other person's done a lot of amazing research. I think he's at Brown University now. And so we survived the prank. A few years later, I know that the students hired someone to come in a gorilla costume during a colloquium and sort of canter about. And one year they put up a big sign outside of the Array Operations Center claiming that the aliens had arrived. So this is again part of the culture of the instrument. It represents that people do the work. And just as a side note, I was reading a little bit of a book on the history of the CIA recently, and it ends up that sometimes agents and station chiefs in the CIA pull pranks on each other just to sort of take a little bit of the air out of their high pressure work. And so it's not unique to astronomy to have these sort of pranks taking place. And I've started to collect different stories of summer student programs where such pranks have taken place. So for example, at the Sunspot Observatory in New Mexico, they have a really amazing telescope called the Vacuum Telescope. It's this huge tower and rotates on a bearing of a pool of mercury, which is just unbelievable to think about. But one year, the summer students put some large footprints down the side of the telescope to make it look like someone had walked up over the telescope. So the field is rife with these, and I think we should collect them all and commemorate them, maybe not celebrate them too much if they're dangerous or hazardous to the instrument, but if they're innocent in some way and just bring attention to the facility, I think it's a fine thing. And I'm proud to have been involved back in the day.
Yeah, I would buy that coffee table book. Observatory pranks. Now, have any of you have worked with students who you've had apply for time on the VLA?
Oh yeah, all the time. I think it's a rite of passage for graduate students to write their own observing proposals with some supervision to start with, and then more and more on their own. When I was a graduate student, certainly my advisor, Jim Cordes, and we quickly developed a division of labor where Jim would write the funding proposals that kept me paid, and I would write the observing proposals that kept us in data. And, it worked out great. And certainly, yes, our graduate students have continued to write observing proposals.
And Amy, how many different wavelength telescopes have you written proposals for now?
It can make for a very busy proposal season, I have to say, because one's done, the Hubble Space Telescope, the Chandra X-ray Observatory, the VLA, all these optical telescopes, ALMA. We just got the ALMA results back. So it's been it can take a lot of your time to try to keep up with proposal writing.
Yeah, between writing proposals for all these telescopes, and again, I've gone through the same set, and then writing proposals for funding to support the analysis of all of this data. It's sometimes astronomers feel like that's their full-time job, is writing proposals. It's a difficult treadmill sometimes.
Right, and you have to have a thick skin because you're obviously not going to get all the time you propose for, and you're going to get some reviews that can hurt. So you have to be willing to take that kind of abuse, and just move past it for the next round.
Well, to end on a less frustrating note than funding, do any of you have any last thoughts about the VLA and your time with it, or radio astronomy in general, or the future of the VLA that you'd like to share?
I just thought I'd make a little comment about the background to my picture, which is a beautiful rainbow photograph taken at the VLA. Doug Johnson, who was an astronomer who had applied for and got his time to observe on the telescope, was observing. I happened to be there when this beautiful double rainbow appeared, and he ran out and photographed it. But my story is that his observation was not very successful because these very heavy clouds, they bend the wavefront out of shape and you don't get a good image. But he was able to copyright the photo he took of the rainbow, and it has appeared in textbooks in electromagnetics and natural phenomena all over the place. So thank you, Doug Johnson, for providing us that beautiful image.
Exactly, and getting the VLA in front of all those people's eyes.
Oh, yes, as well.
I would just say that I think that one of the magic things about radio astronomy and the VLA in particular, because it's so good at it, is that, you know, the things that we're making images of, we can't see with our eyes. The only way we can see them is through the collection of photons from this amazing instrument, the complex mathematical processes that have to go on to make images out of that data. And then the understanding of those images and what they mean through the application of physics. It's just remarkable to me that we can learn so much about the universe through a way that we can't see with our own physical eyes, that we've managed to develop a system to allow us to do that. I think it's really amazing, and it's part of the mystique and the magic of the VLA and the VLBA and all of the other radio telescopes that we have on the planet. And I'm just totally thrilled to see what the NGVLA is going to be able to do. I've been completely floored by the ALMA telescope in Chile, the Atacama Large Millimeter Array, and the images it's been able to generate, just spectacular things. And we're just going to see more and more of this. I remember from my days of giving tours on site, I would cite some statistic, and I'm not sure it's correct, but it seemed correct at the time, was that it cost everyone in America who's a taxpayer basically 50 cents to build the array. 50 cents. And I was like, think about the payback on that. There's been so many amazing discoveries from that 50 cents per person. And although the next generation of telescopes are going to be even more expensive, they're going to generate orders of magnitude more scientific results. And so I just work every day here in Washington and try and promote our field, our discipline, and make sure that the money's there to build these big facilities. And it's an easy sell because the VLA has been so spectacular at performing and uncovering mysteries of the universe. It's been amazing and a very low cost way to expand human knowledge, which is spectacular.
Yeah, I, for one, am glad to hear Kevin say that it's an easy sell, because we professional astronomers, I think, without exception, appreciate that most of our instruments are all taxpayer funded, and that we have this absolutely unique privilege of working at the cutting edge of science and finding all these amazing things about the universe. It is just a very, very special thing.
Right, and we are expecting our astronomy decadal survey to come out in September, and so we'll find out where NGVLA ultimately gets ranked, but I'm very hopeful for it. And of course, the SKA is also incredibly exciting. So it's great that there's a whole future of radio astronomy out there. And I did just want to make one little plug. Carl Jansky actually got his undergraduate degree from the University of Wisconsin back in 1927, and we have scholarships and things named after him. So it's nice for us to have that connection to someone so eminent who has a whole telescope array named after him.
That's fantastic. And oh, Ron, did you want to say something else?
Yes, so I would like to just pitch in and say, and I do believe and I hope that this will stay an international endeavor. So scientists have a common language, a common vision of how we improve knowledge for humankind. And so telescopes like the VLA and the new telescopes in future, where everybody in the world can work together, I think is going to be incredibly important for maintaining global peace.
Well said. And to bookend with your radio rainbow photo, Ron, I am going to share real quick that Hannah texted me earlier this week with a rainbow photo from the VLA. So here's what it looks like now.
Oh, wow.
Or this,
during one of those rare instances of rain.
They're not so rare at this time of year. They're kind of rolling in daily, especially out there. So that's a really great one to end on. But we just have a couple more things. We want to make sure everybody knows how they can get more VLE information and also how they can join us again for our next event. So I want to thank all of our panelists for joining us. Thank you all so much for your time today from all the different locations across the globe, and for just sharing all of your VLA memories and experiences with us.
Thank you. It was a pleasure.
Absolutely. Great fun.
Yeah, that was wonderful. Thank you.
Thank you. So Faith, we will all turn our cameras off and hand it all back to you.
Hello again, everybody. Thanks, Summer. I'm just going to share my screen here once more. And yes, so if you want more about the VLA, we have a lot of different resources available on our website. So our VLA mission control allows you to see what the VLA is currently looking at and the two previous observations that we made before the current one. And it includes the proposals, or at least the abstracts, like the basic description of this is what the project is about for each of those observations. So you can go to the mission control, see what we're looking at, and then click on that the title and learn, oh, well, this is what we're trying to learn about and do with the observations. And then if you want to see what the VLA antennas themselves are currently doing, we have a VLA webcam that updates about every 15 seconds with the latest footage from out at the site. And it's even able to see pretty well during the nighttime too, even though the antennas aren't lit up or anything like that. You can still at least get a decent look at the site out when it's dark there too. And the videos that Summer showed you a few times today are from our VLA Explorer. And so this is a series of short videos that we have that talk about the surrounding areas of the VLA, and some of them go into even more detail than we did here today. They even let you see behind the scenes looks of things that not even all of our employees get to see. So take you into the room where our correlator is located, take you up onto some of the antennas, and each of the videos is just a few minutes long. So you're welcome to go to our VLA Explorer and check all of those out. And if you've enjoyed our virtual tour and would like to learn more and like to continue attending these, our next event is going to be next month, Saturday, September 18th. So the third Saturday of the month. It will again be at 1 p.m. Mountain Time. This time it'll be an hour long, so 1 to 2 p.m. And we'll be highlighting the partnerships that we've done with NASA and the discoveries that the VLA and NASA have made together. So again, thank you so much to our guest experts, to Hannah, our operator, and to our 4 visiting experts, as Summer said, from around the globe. And if you're willing to do so, it would be really helpful for us when you, we have a survey that you can take when you exit out of Zoom that can provide feedback, and that's very helpful for us. And we, like I mentioned earlier, will be sending you an email that has all of the links that we provided. Thank you so much, Montana, for putting those into the chat today, but that will have all of the links that we mentioned so that you can go to our website and learn more. So thank you again so much, everybody, for coming today. We hope you had a great time and have a great rest of your weekend. Bye.
Bye.
Bye, everyone.